Hi, I'm Simon, and today I'm going to talk about later credits, a new technique that you can use to solve your step indexing troubles. This is joint work with Lennard, who's sitting over there in the audience, Joe, Ralf, Robbert, Lars, and Derek. And Robbert and Derek are also here. You can find them if you walk around. I want to start this talk with a question. How do you build semantic models of languages with cyclic features? This could be Haskell's mixed variance recursive types, or Camel's higher order state, so references storing functions, or Java's mutable objects. What all of these language features have in common is that naive semantic models for them are cyclic. And cyclic in the bad kind, where it's not well founded, so not obvious what to do. By now, the dominant choice to build models for these languages is to use a step index logical relation. Where the idea is we cut cycles in the semantic model by introducing a step index, a natural number I, that decreases in each iteration and eventually bottoms out. There's just one problem. If, as probably most people that have ever done step indexing can attest to, you do a step index proof, you have to do a tedious amount of bookkeeping. I've taken a page from a proof here on the right, and I've marked every occurrence of something related to step indexing. And it's important that you do these things, because if you get them wrong, then, well, your proof could be wrong. However, they're usually not very interesting things that you do. It's things like j double prime is strictly smaller than j is less or equal to k minus 2, and you need to show j double prime is strictly smaller than k minus 2. And so ever since the introduction of step index logical relations with their step index arithmetic in the early 2000s, there's been this ongoing push to simplify step index reasoning. The next big step was the introduction of the later modality. That's this little triangle here that hides all those natural numbers and that arithmetic behind the modality in a step index logic. And by now you can use step index separation logics such as VST and Iris, which are machine checked and cocked, so you can actually be sure that you didn't mess up any of your step index reasoning. Now this brings me to the problem that motivated this work. The later modality is a double-edged sword. On the one hand, it's this very powerful tool that logic developers can use to reason about recursive constructions soundly and at a high level of abstraction. In various places, they can put later R, and then their logic will be sound, whereas just leaving off the guard would be inconsistent. However, that's not how the users of these logics typically think about the later modality. If you are in the middle of a proof and suddenly a later modality pops up, well, I don't know about you, but I am typically not filled with joy that I'm now being saved from inconsistency. All I worry about is how to get rid of it. It's a guard, and I want to access the contents that it's guarding. Let me make this more precise with an example that's going to be the running example in this talk. And predicative invariance in Iris. Invariants in Iris are used to share state between multiple threads. For example, multiple threads could agree on the invariant R, and then they can share it between each other. And then each thread can, in a single atomic step, open the invariant, get access to the contents of the invariant, so get access to R, and then show again that after the step, R holds. At least that's how this rule is presented on the first page of the first Iris paper, with a disclaimer that it's simplified for presentation purposes. And what is simplified about it are two things. One is masks, and the other one is later modalities. For presentation purposes, I'm also not going to talk about masks in the rest of this talk, but I do want to talk about the later modality in this rule. In predicative invariance, as the name indicates, can store an arbitrary Iris proposition, including other invariants. And as a result, their model is cyclic, and the developers of Iris have decided to cut these cycles using step indexing. The user of the logic doesn't see much of that, except for the later modality popping up in this rule. And now we come to the tension that I mentioned earlier. for users of the logic, it is kind of a nuisance. So here's a simple example of what you can do in Iris. We have a shared invariant that says, okay, the location L will always store the natural number n, and we want to load from that location. The first step that we do is we use the invariant opening rule, and we get the contents of that invariant guarded by a later. That's what the rule said. And now the immediate next step in the proof is we remove that later. We want to get rid of the later because we need to access the contents that it's guarding to justify the next step. We want to do a load, and the only way you can do that in separation logic is if you have ownership of the location that you want to load from. And how do you do this? Well, you can't get rid of the later modality in general, but there are specific instances where you can. We call this the later elimination problem. We have later R in our context, but we need R to actually proceed in our proof. And before this worked, there were 3 existing options that you could use. The first one is timeless propositions, which are propositions that do not care about step indexing at all, which means you can just remove the later modality in front of them. Then maybe your invariant is not entirely timeless, but there are tricks that you can use. You can use commuting rules to maybe push the later further in across separating conjunctions, existential quantifiers, and so on, until you reach timeless parts, and you can access those. And finally, there's something called program steps, which you can use to get rid of a later modality, but for that, well, you have to step your program. And that is also how internally step indexing is made sound. And these existing solutions are very useful. They work in most cases. For example, for the simple invariant that I showed you earlier, they work. The contents of the invariant are timeless, doesn't care about step indexing at all, so you can just use them. However, these solutions are no silver bullet. There are cases, and admittedly they are rare, but they do occur every once in a while, where the solutions don't help. A very simple example is a nested invariant. So remember, invariants are impredicative. Now we take the original invariant that we had and we put it inside of another invariant. Now the contents of that invariant are no longer timeless. What does this mean for our proofs? Well, if we now open the outer invariant, we're stuck. The inner invariant is not timeless, so we can't get rid of the later modality there. There's nothing to commute, and we need to access the points to before the next program step, so we can't use the stepping rule. So what do we do? Well, you could say that's actually not a useful example, Simon. That's kind of ridiculous. Why would you take that invariant and put that into another invariant? To that, I would say 2 things. The first one is, yes, that example is ridiculous, but it is characteristic of a problem that actually does occur in more advanced use cases. They're just too complicated for slide 11 of this talk. And the other thing I would say is that I was in a situation very similar to this about 3 weeks into learning Iris. I happily nested my invariants. I didn't probably carefully read some documentation that I should have read. And then I was pretty much in that situation. So what did I do? I cried for help. I went to the Iris help desk. That's a chat on Iris where there are loads of very helpful people. And I said, oh, well, I nested my invariants like this, and now I'm stuck, and what can I do? You can do that. The unfortunate thing is the result that you will get in these cases is typically kind of frustrating. So either someone is very clever and suggests a non-local refactoring of your proof, and that kind of sucks because you need to touch a lot of code. That could be you can flatten your entire invariant hierarchy into a single one, then you add a bunch of maintenance stuff that keeps track of how everything relates, and then you redo everything that you already did because like your main invariant changed. Or actually no one comes up with something, and then you can always give up. There are lots of interesting problems out there that do not involve step indexing, so maybe, try one of those. We looked at this, and, well, we didn't like it very much. So we thought, well, can we not develop another option that you can use? And that's what we did with later credits. Later credits turn a right to eliminate a later, so to go from later R to R, into an ownable resource which we denote with this little pound sign here. And that resource is subject to all the traditional separation logic reasoning that you know from separation logic. You can pass them around in pre and post conditions. You can frame them around function calls, and you can share them by invariants. And in the rest of this talk, I'm going to show you what that looks like. In a nutshell, what later credits do is we take the stepping rule and we split it into two parts. One rule that gives us a later credit after taking a physical step. We're basically being rewarded for taking that step. And then a second rule that allows us to spend that later credit for later elimination. If you take these two rules and you put them together, you just get a rule from above. Nothing changed. But you don't have to use them right after each other. You can use earlier steps of computation to justify later eliminations down the road. For example, in this case, we will take a later credit that we get from the addition of 41 plus 1, and we will use it to justify a later elimination when we get to the load of the location L. Specifically, we take one pure step of computation, we get a later credit, and now we use the power of separation logic to say, okay, look, there's a function call, I have some resources, I don't need them for the function call, I want to frame them around the function call, which means after the function call, we still have that later credit. We get to the nested invariant, we open it up, have later of the inner invariant, and now we can spend that credit to get rid of the later modality. And suddenly we just have our invariant that we had earlier in the example. And from here on, the proof is pretty straightforward. So this is what we call prepaid reasoning, and that's what later credits enable. And we looked at this and we thought, well, can we maybe scale this to even more? And one example that I want to discuss in this talk are prepaid invariants. As you might have guessed by now, our life would be a lot simpler if there were no later modalities in that rule. So before this work, I went to the experts and asked, well, can't we just remove the later modalities? They were like, I don't think that's sound. Right? So let's see what happens when we put later credits into an invariant. The idea is relatively simple. We build a new kind of invariant that stores the contents that we want and a later credit. And then when we open that invariant, we have that later credit in hand, so we can use it for later elimination, which means we get direct access to the contents of that invariant. And then we need to put one later credit back that is generated by the next step of computation. In fact, we can actually generalize the later credits mechanism a little bit to generate more than one later credit per step. And we do get the full rule where there's no later here, but we also don't have to put a credit back after the next step. And with that, I want to start to wrap up. There's more in the paper that I didn't cover in this talk. For example, we have applied later credits to two larger examples. We did a logical relation for reordering, including reordering some higher order stateful operations of a promised data type. And then we also did some logical atomicity proofs. As a quick side note, logical atomicity is how you prove linearizability in Iris. And when you do that in Iris, it's very easy to get in tricky step indexing situations. However, with later credits, we could simplify those. We tackled a challenging counter, and we were able to simplify the notion of logical atomicity in Iris. We proved the soundness of the entire mechanism, and as I mentioned earlier, we developed extensions and also discussed sort of what they mean, because you can also generate more than one later credit per step. And with that, I want to conclude. As I promised in the beginning, later credits turn the right to eliminate a later into an ownable resource which is subject to all the traditional separation logic reasoning. As we've seen in this talk, we can pass them around via pre and post conditions, we can frame them across function calls, and we can even put them into invariants. If you want to use them, they're now part of Iris by default, and they have already been applied by multiple ongoing projects. Thank you for your attention, and I'm happy to take any questions you may have.